Carboxylic acids. They are a homologous series of organic compounds and are very important organic chemicals. Important but weak. Upon breaking down, they form esters, another important substance. Often used in the fragrance and flavor industry, esters are pleasant. Without them, we can't cover up for our body odors, the flowers won't smell pleasantly, and the fruits wouldn't taste fruity.
Even if we know that esters are a derivative of carboxylic acid, the two are distinctively different in terms of their properties. The most noticeable difference is their smell.
Carboxylic acids are not really that pleasant. In fact, you can blame them for the taste of vinegar, the smell of sweaty socks, and the taste of rancid butter.
Even if these scents are kind of sensitive and strong, the acids are weak. They have higher pH and are less reactive compared to the strong acids. Here are examples of some reactions.
A carboxylic acid that reacts with a metal would result to hydrogen and a salt product.
A reaction with soluble hydroxide would result to water and a salt product.
And an acid reacting with the metal carbonate would result to salt, water, and carbon dioxide.
Esters, on the other hand, are the total opposite. They contribute to the greatest smells of nature. Here are a few examples. Ethyl butanoate serves as a strawberry flavoring.
Methyl salicylate gives us the oil of wintergreen, a known group of aromatic plants.
Isopentyl ethanoate is the tropical aroma of the banana.
Methyl transcinnamate is the very nice smell of strawberry. Since ester is a known derivative of carboxylic acid, we must know just what kinds of reactions take place for this to occur.
Alcohols, when added to carboxylic acids, is called the carbocation mechanism. The process of forming an ester linkage between the acid and the alcohol is known as esterification.
Esterification is a flexible process in nature, which is why some experts prefer to use carboxylic acid chlorides and carboxylic anhydrides in the process. They usually result to higher product yields of ester. To speed up the process, it is highly preferred to use concentrated sulfuric acid as a catalyst.
Esterification is reversible. So, to form a carboxylic acid with alcohol as a bonus, you just have to reverse the process via hydrolysis. Carboxylic acids, together with esters, are present in fats and oils. These fats comes in different forms and has various functions such as energy storage and insulation to our organs. The salts of carboxylic acids are known to be very useful. Sodium and potassium salts are used as soaps. Calcium and sodium propanoate are used as derivatives in bakery products. Sodium benzoate can be preservative for sodas and ketchup. A mixture of sodium citrate and citric acid is widely used as a buffer, which can be found in jelly, ice cream, candy, whipped cream, medicines, human bloods for transfusions.
Esters are present in numerous molecules that can be used in commercial and synthetic application. Polyester molecules make excellent fibers and are used in many fabrics. A polyester tube can be used in surgery to repair or replace diseased sections of blood vessels. PET or polyethylene terephthalate and other esters of low volatility are used to make bottles. Some esters are also used in mylar tape for cassettes. Other esters are highly used in cosmetics and perfumes. And some volatile esters are used as solvents for lacquers, paints, and varnishes. In this example, you must begin counting at the carboxylic carbon. It is located here. This will be number 1. Since the structure has no branches, which are substituents, counting will continue until the very end. The chain ended with 7. According to the chart, the prefix for 7 is hep. Originally, the word was heptane, but the structure is not an alkane, so the suffix will be changed to oic, giving us heptanoic acid. This structure has a branch, so we must try both branches and count the longer chain. The first chain going downwards has 7 and the other has 8, so we'll have to go to the longer one. At the 6th carbon, there is a substituent. Since the substituent only consists of one carbon, its prefix will be meth. Ane will not be its suffix because it's just a substituent, an alkyl. The suffix will be -il. In naming, the numbers are stated first. And remember that numbers and words are separated by dashes, and numbers to numbers are separated by commas. In this case, the alkyl will be 6-methyl. Octan will be the prefix for the main chain, and the suffix is oic. All in all, we have 6-methyl octanoic acid. There are no branches, so counting will go on. It ends with 6, giving us the prefix of hex. At carbon 2, there is a double bond. Its proper affix will be -in. This is why the prefix for the main chain will only be hex. When the two affixes are attached together, they form the word hexene, and this corresponds to the nomenclature of alkenes. But because there is a triple bond at carbon 4, the -in affix will have to lose its last letter, to be replaced by the proper affix for triple bonds, -ine. Lose another letter again, and add oic to complete the word hexeninoic acid. Since there are locants for the bonds, they should be placed before the affix. Remember to incorporate the dash comma rule, giving us hex-2-n-4-inoic acid. It is possible to have carboxyl groups at both ends. Since there are no substituents, you can start counting from either carboxyl group. The last number is 5, resulting to pentane. Since there are 2 carboxyl groups, the suffix will be dioic. As you can see, the suffix starts with a consonant, which is why we don't have to remove the E in pentane. Let's split the naming process into 2 parts. Let's start with the alkyl group. The count ended with 3, giving us propyl. Remember that this is an alkyl group, so it is not named as propane. In the carboxylate chain, start counting from the carboxylic carbon. It ended with 4, giving us butane. Since this is an ester, the last letter of butane will be changed to O-weight, giving us butanoate. All in all, the result is propyl butanoate. In this example, it is shown that it is not necessary that the carboxylate group is the longer chain. It is possible for the alkyl to be longer than it. Starting with the alkyl group, counting the carbons gives us 8, so the alkyl is octyl. For the carboxylate group, start counting at the carboxylic carbon. It ended with 5, giving us pentane. It has a triple bond at the second carbon, therefore modifying the chain to be pent-2-inoate. At the fourth carbon, there is a methyl present, giving us 4-methyl. Combine everything together and get octyl 4-methyl pent-2-inoate. Let's start with the alkyl once again. This can either be seen as an ethyl with a methyl substituent, or one propyl with the second carbon as the linked carbon. Let's take the first possibility. Since the methyl substituent is at the first carbon of ethyl, you can name it as 1-methyl ethyl. The second possibility looks much simpler. You just have to specify the locant of the linked carbon. Instead of propyl, It will be named as propan-2-il. The carboxylate only has 2 carbons, so that gives us ethanoate. Join the terms and you can get 1-methyl-ethyl ethanoate or propan-2-il ethanoate.